All right, so this morning we're going to talk about RosettaScripts and and within that talk about movers. So like I said, we're going to get kind of a general overview of RosettaScripts, go into sort of how the movers and filters are written, talk a little bit about singletons and abstract factories, and how to add a mover to RosettaScripts. So who has used RosettaScripts before? Awesome. Yeah. So we have a lot of people are familiar about it. That's cool. So if you aren't familiar with RosettaScripts, this is a pretty short RosettaScript example. So this is written in XML. So you'll have your different sections. And since not everyone raised their hand, I'll kind of go through it. Sort of the way you read a Rosetta script, if you're looking at this, is starting in the protocols section. So sort of read it from the bottom up. So these are kind of what's actually going to be happening when you run your Rosetta script. So it's going to go through, so it runs this first mover that's listed. So the mover name is design. So then you would go back up and you would find the mover that you named design. So we're saying like run the design mover. Well, what is that? We named this pack rotamers mover design. So that name is whatever you want to call it. The name equals, that's, you decide whatever you want to call that. It can be, you know, any string. And that's going to call the pack rotamers mover on the pose at that moment. So then after it runs the pack rotamers mover, it's going to go to the next one. So it's min. You go back up into your script. What is min? And you named that the min mover min, and then you have different parameters that you're setting for that. So that was a pretty simple Rosetta script. If you've ever looked into some of the other papers that are using Rosetta scripts for these really complex protocols, you can get really, really long Rosetta scripts. So both of these are totally valid. So we have something pretty simple. You have like a quick protocol that you want to run, you know, something maybe in a bigger pipeline, and then, or maybe you just want to score something. But you can really, RosettaScripts gives you a lot of flexibility to really piece together a lot of different pieces of code in a way that you want to without having to write a new application in C++ and, you know, recompile and you know, it just gives you this flexibility to access a lot of these chunks of code that have been written in Rosetta, and then you piece them together how you want. So movers are really the basic unit of any protocol in Rosetta. So anytime you're thinking there's some manipulation you want to do to your pose, you should be thinking, is there a mover for that? So, and if there's not a mover, then you'll write a mover for that, for what you want to accomplish. So all movers have this virtual method apply, which takes a pose as an argument. So that means when you are writing a mover, you have to define this apply function. So all movers have this apply function. And so any mover is essentially inherits from a base class mover. And since this is a pure virtual function, all of them have this. So then that gives you the flexibility of later on in the, like somewhere else in the code, you can just have this base mover type. But then when it reads that, it will, when it calls the apply function, it will go to like the most child class. Is that, I feel like child's not the word there. Yeah, the most derived class. That's yes. So it will use the most derived apply function there. So the idea is essentially you're going to hand a structure to the mover. That mover does something and then hands that on to the next step of your protocol. And I will say So we have like hands a structure, but it really hands it a pose, right? And we talked about yesterday, a pose contains structural information, but what else does it contain? Energies, yes. So you can use movers to both manipulate the structure, but also maybe doing something with the energies, right? So scores or adding constraints. So the big pro of this is this of movers is this gives us this uniform interface for a really wide range of possibilities. This could be a little bit limiting, so there's there's a little bit of a constriction there of like, especially if you're thinking about using like RosettaScripts, maybe there's something you want to do that doesn't quite fit that manipulating a pose, which is then motivate you to write some C++ code. But in general, I think RosettaScripts are pretty like a little bit lower learning curve and really flexible, and you can build some really cool protocols with that. I guess I just said this. So movers change a pose, and that's not necessarily a conformational change. So there's a score mover or a constraint set mover. And then these movers can be so that you can have sort of nested movers where, let's say you have a protocol that or something in mind that you want to run, where if some condition is met, you want to apply one mover, and then if a different condition is met, then you want to apply a different mover. So this would allow you so you can kind of wrap movers into the code like that. So like I said, movers are inherited from the base class protocol moves movers, which is found in src protocols moves mover.8h. And the apply method is really your main method that's going to do the bulk of the work there. But you will note that the apply method only takes one argument. So it only takes this reference to a pose. So you'll have to, if there's any other parameters you need, you'll have to set those up in your mover class through member variables. So if there's some kind of, you have a loop and you have a number of iterations, so that's something that you'll see today in your afternoon lab. There are some other functions that need to be set. So your afternoon lab will kind of go through those, but these are, like I said earlier, these functions are set like this in your base class, where they're virtual functions and they just have like equals 0. They don't have a definition of what to do for that function. Those are the pure virtual ones, and that means your inherited class, or sorry, your derived class has to set those functions. So your code won't compile if you don't define those functions in your child class. So one of those is get name. And I feel like there's one more, get name and apply, but maybe I'm wrong on that. And then there's other virtual functions that you can override, but you are not like absolutely required to override. And then there's also functions that if you want your mover to be compatible with RosettaScripts, that you also need to define within your mover class. So that would be parse my tag, clone, and fresh instance. So by default, like if you don't include those, your mover could like not be accessible via XML. And maybe you're like, well, I'm just writing this mover for like a C++ application and I don't really need it to be XML. I would say as like someone that's wanted to move or to use movers in an XML script that weren't set up for that, I was like pretty peeved about it. And at the time, like didn't understand enough to know that like I probably could have added stuff to that mover to make it compatible with XML. But I think that like it just gives your code that you've written more flexibility to be used by the rest of the community or people outside of the community even. All right, so like I said, the kind of workhorse of your mover is going to be the apply function. Um, so like later today when you're writing your own mover, a lot of the code you've already written for your application or for your protocol, you're going to stick into this apply function. All right, and I think we've mostly gone over the rest of this. So it modifies the pose. Any other parameters have to be initialized before your apply gets called. So here's an example of a set torsion, a hypothetical mover. So you would have your class. So we have it called set torsion, and it's going to inherit from mover. And then you would need to define apply. So it would go through and do, whatever work you wanted to do in your function, you have here in apply. So it goes through and checks which torsion angle you want to change and then sets that torsion angle. In Python, that would look more like this. So just a different syntax for how you're setting up your class. So you have set torsion and it inherits from protocol moves mover. And then you have a similar, you would define your apply function and then run through that. Another example is the clear constraints mover. So at the top is what this could look like in C++, and then at the bottom is what that would look like in Python. So very similar, right? We're inheriting from the mover class. So this is like the whole apply function, is this remove constraints. Why would we not just, if we wanted to remove the constraints, why do we need to write a mover for this? Or why would we potentially want to write a mover for this and not just like in the code call remove constraints?
We might want to remove constraint as a specific step during another mover.
Exactly. So there might be a specific step that you want to remove those constraints, and including it as a mover allows the flexibility of putting that into a larger protocol, right? Like we looked at the nested, like nesting movers earlier. So you could have, if some condition was met, now we want to remove those constraints and run some other mover on that. All right, so like I said, we have the nesting movers. So one of those examples is the sequence mover. So this would essentially add a pointer to a mover, and that could be any. So that could be any mover that's set up. You could essentially plug in any mover here, right? So the code just has the base class, but that would then look at whatever mover was set up when you initialize this. So here's your apply function for this. So this goes through, like, you could have many movers in this and loop over those and then see how that's changing your pose in some way. So if we define a new mover in bootcamp mover, which is in protocol 7, like we have that in protocol 7, sequence mover is defined in protocols 3. Do you need to recompile sequence mover if you want to pass an instance of bootcamp mover to call sequence mover, the sequence mover add mover? If you're writing in bootcamp mover and you're using the sequence mover in your bootcamp mover, do you have to recompile sequence mover if it's in protocols 3? No. So that's kind of a benefit of this, of being able to build these protocols without touching some of the other code and not having to recompile that. So if you, like I said, there are certain functions that you need to define if you want to use these within RosettaScripts. So one of these is parse my tag. So the utility tag tag class is going to have the essentially the options that you're setting in that XML script. So if you think back, most of you said you had experience with that. With using XML scripts at least, or maybe writing them. So those options that you put within your tag for your mover, you set those. Those are going to be read in through parse my tag. So that's going to look slightly different if you're writing in C++ or Python. So this is kind of an example of what that looks like for the forced disulfides. So you could have various tags that you want to read in. So maybe you have your score function. You need a specific score function. Which residue pairs? This is the forced disulfides. So you would want your residues that are involved in that. And then you're going to go through and set those. So this will be, you'll kind of walk through this process in your afternoon lab today for how you implement these tags. So there's also filters. Has anyone worked with filters within their XML scripts? A few people. So the purpose really of a filter is to kill a trajectory that is not going to be useful at the end, right? That's kind of headed down the wrong path. So filters are going to look very similar to movers. You'll have this apply function, and if it returns true, then the post passes and kind of moves on through the protocol. If it returns false, then that kind of instance would fail, and you would start back with a new round. So filters, I don't think we get much into this. We talk about simple metrics later, but some filters, I will say, if you guys have much experience in looking at these, are not always necessarily used to kill a bad trajectory, but sometimes used to like output a value that you're interested in, like some metric. I think most of those have been moved to simple metrics, and that's definitely like if you're thinking like I want to write something that outputs some value, like some metric that you want to use to analyze some data. We recommend writing those in simple metrics, and we'll look at that later. But sometimes just like simple metrics sort of came after filters. So there are filters that don't have that are just for like spitting out data, but there's not a simple metric that corresponds to that.
Were they stored in filters because like the structure is similar for like what you need to do to get those values? Like
yeah, it was just like an easy way, like
it was just the easiest thing to do for simple. Okay.
Yeah, at least that's my understanding. Simple metrics existed when I started, but there are like you'll be looking back at protocols and someone will be using a filter to like output some kind of score. So that's something you might see, and don't be confused about it if you see that. So these to use within RosettaScripts are going to look very similar to your movers. So you're going to use your parse my tag and input the different data that you need into that. We already went over that. All right, so if we took the script we had before, we could add a filter to that. And essentially, so how this would now work, so we added a filter to the pack rotamers step, so design, pack rotamers mover. So we have a pose, we run it through pack rotamers mover, we check the score type filter, and if that passes, so if the so we have the our filter in this case is testing total score, and our threshold is -120. So if that's true, then we go on and we do minimization, and if that's false, then we go back to the original pose and we run through this again. So, there's different design patterns that have been, or there's different patterns, I guess, that have been designed that are kind of a set of known solutions to challenges that happen frequently in software development. So these, one, provide a common language that makes it easier to communicate, like if you're following a design pattern to solve this problem, then telling someone else that's also a developer, like, oh, I used, such and such pattern, then it might be easier for them to like understand what you're doing, and you guys are sort of speaking the same language on that instead of like going through all of the details of what you've done. Or if you have this problem, someone ran into it before, they have this design pattern, then that can give you sort of a guideline of how to solve your problem. And these different design patterns are found all over Rosetta. However, I'd say, like, if you have the same problem or a similar problem you think you can solve with a design pattern, you don't need to necessarily design your code to fit the pattern. But if you know about these common design patterns, it helps you solve those problems. So if you kind of go in and be like, okay, what are the concepts here? How do they solve this? Why does that work? Then it would help you design your code. But you don't necessarily be like, oh, I've already fixed this problem in this way. It's slightly different, than this design pattern, so you need to go back and like fix it, right? So it's good to know about them and to use them to help you, but I wouldn't stress about making sure it fits like every single definition of that problem or that design pattern. So one problem we run into is if there's large read once data. So if you had like a big file that you need to read in and you need to use data from that file in a lot of different contexts, you don't want to have to read in that data more than once. So you want to read that data in once, and you don't want to pass that data around as an argument to every single function that you're writing. And this data is never going to change. So for that problem, there's the singleton design pattern. So a singleton is a class, like essentially a class that only has one instance of that class. So this has kind of a common pattern of you're going to have this a private pointer for instance. The constructor will be private so that other things can't create more instances of this than one. And then you have this get instance that essentially checks to make sure if an instance already exists, then it doesn't create another instance. So what does that kind of look like in the code? So like I said, you have a private constructor, and then you have this get instance. It checks if there's already an instance, and if not, then it creates that instance. If there is already an instance, it returns the one that already exists. So there's multiple examples of singletons in Rosetta. So the job distributor, scoring manager, chemical manager. We're going to talk about or you're going to have a little bit of experience with the mover factory as you guys work on writing your mover. And the filter factory is very similar to the mover factory. So a challenge we have with RosettaScripts is that we need to construct these objects or these movers or filters or simple metrics or whatever it is in your XML script from a text file. So how would we do that? You could imagine that there could be like one solution that you have, like, oh, if the string in your XML script is if it's pack_rotamers mover, then we create an instance of the pack_rotamers mover. If it's clear constraints, then we connect that. Has anyone looked at like through some of the protocols files and seen like, are there like 10 movers, maybe 20 movers in Rosetta? There's a lot of movers. I don't actually know how many there are. That would be a cool fact to add on this. But you don't want to have this giant if block that's like going through every single going through every single possible mover. So how do we solve this problem? So Rosetta uses this abstract factory design pattern, which is essentially a pattern that's for creating objects. So these abstract factories have little to no private data and are useful if you need to initialize objects or kind of manage the creation of these. And these are also used kind of all over the Rosetta code. So what does this look like? So essentially, if we think about this as like the mover classes that we just talked about. So if you have your base class widget and then you're writing like my widget, that's kind of like, this is like the main thing that you're thinking of, like, I need to have this class defined. But then how do we connect that to the text file that you're going to provide for running your XML script? So we have a creator base class, and then you have you inherit from that to create your my widget creator, and then the factory really connects that registration to your creator class. So you would call within the factory, you would call your the widget creator, and then that's gonna connect it with the factory. So you have widget, like I said, that's you could kind of think about this as like the mover. So that's going to be the productive class. It's a pretty heavy class, or it could be a heavy class. Then you have widget creator. So that creates the particular widget. It knows the name of that, which is important to connect connect the string to the name of what you're trying to create. And it doesn't depend on the option system. Then we have the widget factory. That's our singleton. So there's only one instance of the widget factory. And that kind of holds the map from strings to the creators. And then your widget registrator, which ensures the creator class gets hooked into the widget factory at load time. So what files are involved in this? So when you can think about this as also like what files you're going to be making for your mover. You have your class, my widget, inheriting from the widget class. So you have a forward header, a header file, and this is, sorry, I don't have my little C++ thing here, but it is important, I think, even if you're writing in Rosetta, to know what these files are. So when you go in and you're like, oh, I'm looking for, whatever mover class, I'm like blanking on all movers ever right now. But if you go in and like, you're looking for the add membrane mover, and then you find the add membrane mover where it's at in the code, and then you're like, what is a forward header, or like fwd.hh? Like, where do I need to look? If you're, you're writing in Rosetta, but you need to sometimes look into the C++ code. You might be like, where do I need to look to figure out what this mover is doing? Now you're going to know when you look at this where are you going to find the meat of what's going on in a mover. Like, we've kind of talked about it, talked about the different functions and files. So I think the C++ folks probably have a pretty good idea. But of these files, so let's say you have a class called myWidget, and you're looking, let's say it's a mover, so it has the apply function we talked about. Where are you going to look for what that apply function is doing if it's not clear from the documentation? Any ideas? You guys can just guess.
The header file, and if that doesn't have any comments written, then you just look at the code itself in .cc.
Yes. So the header file is going to have the declarations of the function, so you'll see that applies there. And then the actual like gory details, like if you get into that and that's not telling you enough information, and you might be able to find just comments in that file, in the header file, to get enough information. And if that doesn't have what you need, then you can look at the .cc file, which is going to have the actual function definitions. So you could go to your .cc file, dig into the apply function. That's what you're going to look for a mover, and then see what the actual steps are. And that kind of gives you an idea, like if you could find the apply function for the mover that you're interested in, you could copy and paste the apply function that's written in C++ into whatever Gen AI you want to use and say, like, walk me through step by step what's happening in this apply function. It's going to be hard to go from like having no idea where to look for this, but I feel like if you get to that point, then you might have a better sense of what's going on and be able to find that. So yeah, these are all the files you're going to need for creating this a class and being able to use it through the abstract factory. So these are different usages in Rosetta for this design pattern. So kind of to sort of summarize, what do we need when adding a mover to RosettaScripts? So if you're writing this in C++, you'll write your mover, you'll have the apply function and parse my tag and the other functions that are required to write your mover. Then you'll need your forward header file, your header file, and your CC file. So you'll write the mover creator that inherits from, sorry, you're right, like my mover creator that inherits from mover creator. So you'll have the my mover creator header file, and then you'll need to register your creator within the mover factory. So there's going to be in protocols init, you'll have these mover creators .ihh, and you'll define an instance of your mover creator in those files. And then for PyRosetta, on one hand, this might be a bit more simple for all the steps of creating your mover, but I will say, like, if you're writing a mover in C++, there's a lot of different examples you have to look at for, like, there's a lot of examples of movers that have been written in the Rosetta codebase in C++. There's not as many examples that you can find of movers that are easily, at least findable on GitHub, that have been written in PyRosetta. But it's a very similar process, so essentially you need to go through all of the same steps of the mover that we talked about for C++. So you'll write your mover, you'll have definitions for those, the pure virtual functions that I talked about, and also the functions that are required for it to be set up with XML, so such as apply and parse my tag. Then you need to have a creator, so my mover creator, just like we did for in the C++ code. You have more flexibility here, that you can define this your my mover creator in the same file or in a different file. I think it just would depend on how you're setting up your code base, how, what works best for you. And then you'll need to register your my mover creator with the mover factory. So like I said, this can be in the same file, it can be in a different file. And you will have this global variable that holds a list of all your mover creators. And then you'll append my mover creator to that global variable, which is sort of doing the job of some of the other files we saw earlier for the C++ code.